Only a 30-minute seminar, but because I was going to give a tutorial today, we extended it to an hour. So what I'm going to talk about is modern electronic warfare in the 21st century. And if you look at sort of the application space of EW, electronic warfare, there are three main components: electronic attack, electronic protection, and electronic support. And the terminology has changed over the years. This used to be electronic support used to be called ESM, electronic support and measures. EP was something else. That was electronic countermeasures. So anyway, this is the current terminology that's used, and it impacts the radar domain, and it also impacts the intelligence domain. And so in intelligence, we have SIGINT, which is signals intelligence, and under SIGINT in the EW domain, we have ELINT, which is the collection of radar signals, and COMINT, which is a collection of communication signals. And this just gives a kind of a quick snapshot of what EW is all about. It includes techniques that are exemplified by hard kill. There are the use of flares for infrared countermeasures. We use chaff to confuse radars, and we use jamming energy, electromagnetic energy, that's delivered to the radar to confuse the radar. So one of the things that electronic warfare is used against is an integrated air defense system. Integrated air defense system takes all of the sensors that are used against attacking aircraft and integrates them. So radar, visual observers, other technical means, and anti-aircraft weapons, which could include anti-aircraft artillery, surface-air missile systems, airborne interceptors, etc. And it's under a common system of command, control, communications, and intelligence. Oh, by the way, if you have any questions as we go along, just go ahead and shoot. Depending on national doctrine, control is more or less decentralized. Well, in NATO, traditionally, for a fighter aircraft, the fighter pilot has the ultimate authority to pursue the final attack. In the old Soviet doctrine, it was much more tightly controlled. The pilot didn't really have authorization. He or she had to get permission from his command center to make an attack. And so today's air battle really is a duel between the IADS and the SEAD, which is Suppression of Enemy Air Defense Campaign. I'm sorry for all the abbreviations and acronyms, but that's part of the game. So if you look at how an integrated air defense system, IADS, functions, it has a kill chain. And it starts with the early warning, the very long-range radars that do search and early warning. And that does initial detection. And then those radars will pass information, tracks, over to acquisition and ground control intercept radars. Acquisition radars will hand them off to SAM systems and other kinds of ground-based systems. And then the GCI, or ground control intercept, will vector a fighter into that attack formation. And so then there's target engagement and weapons delivery, and this is all controlled by this command control communications network. If we look at there's another sheet up here. If we look at with the UK, US, Western forces, frequently the kind of surface-to-air missile systems that we would be competed against are Russian-built. The Russians have a history of building very good surface-to-air missile systems. Start off with SA-1, SA-2, and now it's down to SA-23. This is an SA-2 system. It's the radar is called the Fansong, and it consists of two antennas that transmit. One transmits a fan beam that's horizontally oriented, and it sweeps in the vertical, so it measures altitude of the target. And then one sweeps, it has a fan beam that's oriented in the vertical, and it sweeps horizontally, so it gives azimuth information. And then these are our auxiliary systems. This is a missile control system. It has a separate RF link to the missile, so it provides command guidance to the missile as it goes to the target. This is just this is an old system, but it's the basis for almost all of the current Russian systems. So it's a good system to look at. The missile is called the what is it called? The Vina is what the Russians call it. Guideline. The NATO name is Guideline, and the missile has an S-band fuse in the nose of the missile itself. So when the missile, the fuse is oriented off to the side of the missile, and so as the missile approaches the aircraft, it doesn't have to hit the aircraft to detonate. If it gets close enough for the fuse to detonate the warhead, it'll detonate. And the warhead has a large number of ball bearings that are made out of steel. And those things explode into a big donut shape. And it's a very lethal system.
So the S-band system is sideways looking, and see if it's in proximity of the target, not straight on it, and then that will detonate if it's close enough. Is that what you're saying?
Yeah. It's a fuse. It's an RF fuse.
Right.
So what it does is it radiates out like this.
Right.
In a sort of a donut shape. And if it gets close enough to the aircraft that the fuse says, okay, detonate, then it'll detonate and will launch out this warhead.
Okay.
With ball bearing. The missile's range is 17 nautical miles. Its maximum altitude is around 60,000 feet. And this system, most of you guys are not old enough to remember this. Almost none of you are. A few of us are. But the Russians shot down an American U-2 in 1960. The pilot's name was Gary Powers, and we thought that we were flying above, the capability of that system, but we were wrong. We were not flying above. And then, as I mentioned before, there's the two radar systems: elevation scan, azimuth scan, and then it's got this dish antenna that transmits this is an L-band signal. It transmits guidance signal to the missile. And then the tracking system, besides tracking the aircraft, it tracks the missile as well. It's called a trackball scan system. It's got the two beams, and it ideally, when it locks on a target, it gets the target right in the middle of those two beams. And the system is pretty robust against countermeasures. So, if you look at air defense threats and the kind of targets that they typically engage, we've got radar-guided weapons. Radar-guided weapons usually are used against aircraft and ships, occasionally against ground mobile targets, not normally used against fixed sites. We have laser-guided weapons. Not normally used against aircraft, occasionally used against ships. More often going to be used against ground mobile sites or fixed sites. And then heat-seeking weapons, which are frequently used against aircraft. Lethal communications are used against aircraft, fixed site. And when we talk about lethal communications, what we're talking about is a command and control center that's talking to some kind of weapon system that's going to engage the aircraft. So it could be an airborne interceptor. If we look at the way that the missile systems are guided, here's 4 common kinds of guidance approaches. One is so-called active homing, which is a monostatic technique. So the missile has its own radar, and the missile's radar locks on the target and then tracks the target and then flies to the target, tries to engage it. Then we have semi-active, which is a bistatic approach, and in that case, we have an illuminator, which can be another aircraft or it could be a ground-based radar that's illuminating the target, and then the scatter from the target comes back to the missile. The missile has a passive seeker that locks onto that reflected signal from the target, and then locks on and then homes in on the target that way. And then we have passive homing systems, and they're exemplified by like infrared. And so, a common type of air-to-air missile is an infrared guided missile, and it just locks onto the infrared signature of the aircraft and homes in on it. And then we have retransmission homing, where we have a more complex system. We get scatter from the radar itself to the missile, but then we also have an uplink that controls it. So it's a sort of a hybrid system. We think about SIGINT, which stands for Signals Intelligence, and SIGINT is comprised of 2 subdisciplines. One is ELINT, Electronic Intelligence, and ELINT is it really deals with the intercept and analysis of radar signals. So if we have specialized aircraft, I'll show you a picture of one in a minute, specialized aircraft that go out in the combat zone, or it could be just flying reconnaissance basically around Russia or China or somewhere. And the aircraft have specialized receivers that receive the radar signal, and they use that signal to find the location of the radar. One of the important things is where is that radar located, and then they also look at the different modulations the radar has, the RF that it has, what its beam shape looks like. They try to infer all the parameters of the radar, and if it's a known radar, if it's operating in a mode that we haven't seen before, that's good intelligence information. If it's a radar that they haven't seen before at all, that's really good information. And then just finding out the location of radar is very important, especially if it's a SAM associated radar and you're in a combat or near combat situation. And then we have communications intelligence and comment, and it's really designed to do the same sort of thing we're talking about with radar, with ELINT, but it does it with communication signals. And the communication signals could be data communications or they could be voice communications. And frequently, we have specialized aircraft that have operators that speak various languages that listen to that. If it's a voice signal, they listen to that voice signal and then record what's going on. Both ELINT and comment are really heavily dependent on digital processing. Nowadays, all the electronic warfare systems are very dependent on digital processing. We have, in both the ELINT and comment case, we have a library of different parameters for radar systems and for the communication systems. And the processing typically involves 3 stages in series. So in the ELINT case, we sort the radar pulses as they come in. We segregate the pulse trains. So we got, if we're in a dense pulse environment, we have lots of different radars that are illuminating us. Then we want to be able to separate out the pulse train from those various radars so that we can analyze that particular radar. So we segregate the pulse trains. We do the direction finding to locate it. And we do discrimination of the emitter waveform parameters and identification of the emitter. So waveform parameters could be pulse width, pulse repetition frequency, any modulation on the pulse, etc. And ultimately, we want to identify the emitter. So this is a piece of hardware. This is a RC-135 rivet joint, and both the RAF and the U.S. Air Force fly this aircraft. It was modified by E-Systems, and which I guess was bought by L3 Communications, actually, Greenville, Texas. And this was delivered to the RAF in 2013, and it shows it landing at RAF Waddington. And this airplane is a very competent SIGINT aircraft. So it's going to do ELINT and comment. It's got a whole raft of operators back to back in, and plus it's got all kinds of automated equipment. And you can see it's got a SATCOM on here. You can see the radar, the antenna farms all over the aircraft. So if you look at how we employ SIGINT systems, and so ES is electronic support, and when we think about it from kind of a more tactical, more immediate response, we usually use the terminology electronic support. When we think about it from a more strategic point of view, we use the terminology SIGINT. And but the process is pretty much the same. It's just that with electronic support, we're trying to find out things very quickly to get it to the battlefield commander so that he can give the information to his strike forces. With the SIGINT system, it's more of an intelligence process, so it's a longer term, more detailed analysis kind of process. So we intercept and process signals from hostile emitters, we extract the required information and output the data to other assets. Differences in the types of antennas, receivers, and processing. So if we look at our system, we've got an antenna. Typically, we've got an antenna in an array of antennas. We've got a receiver. We've got an array of receivers. We've got a processor. We've got an array of processors, and then the data goes out. So to enable systems like that, we have to have specialized electronic warfare receivers. And so it turns out that there are a number of different kinds of EW receivers. This shows a few of the most common types. The crystal video receiver is a fairly inexpensive receiver. It's got relatively low sensitivity, It's typical EW applications in a radar warning receiver. It's performance. It's got wide frequency coverage. It's very broadband. It's got fast response time, but it can only process one signal at a time. There's another kind of receiver called an IFM, instantaneous frequency measurement receiver. Again, it has fairly low sensitivity. Again, it's used primarily in radar warning receivers. We haven't really talked about radar warning receivers. I'll talk about them in a minute. But those are typically mounted on tactical aircraft to give immediate warning of threats. The IFM can give you up to an octave of frequency coverage, and it, again, only works one signal at a time, and it really only measures RF. Super heterodyne receiver is a much finer grain receiver. It has medium to high sensitivity. It can be used in radar warning receiver, ELANT receivers, electronic support receivers, and targeting receivers. And it selects one of multiple signals and recovers any modulation. So super heterodyne can give you, it's a more expensive receiver. It can give you a lot more information. It's used in a lot of, typically, especially in ELANT and ES. Channelized receivers have medium to high sensitivity, and again, they're used in radar warning receivers, EW and reconnaissance systems, and they're specialized for complex signals. They can process multiple simultaneous receivers, and they can recover, complex modulations that are on the pulse.
So it's an RF.
Yeah.
That's an RF channelization.
Yeah. Mm-hmm. Yeah. Exactly. The digital receivers give medium to high sensitivity, and they're used in every type of EW reconnaissance application. Give wide frequency coverage, fast response time, but again, only one signal at a time. Okay, so I promised I'd talk about radar warning receivers. This is a typical installation of radar warning receiver. Radar warning receivers were first used in the Vietnam War back in the 60s. And they were invented because in the bombing campaign against North Vietnam, the Russians had given the North Vietnamese a really solid integrated air defense system. Had this SA-2 radars, missile systems. And when the U.S. Air Force, U.S. Navy first started bombing up there, lost a lot of aircraft to SAMs. And they had no warning receivers, they had no countermeasures basically against SAMs. So one of the first things that was done was the development of the radar warning receiver and installation of those kinds of systems onto the fighter aircraft. And this shows just a notional schematic. Typically they have 4 antennas, and they're mounted on the horizontal plane at 45 degrees. So 45 degrees off the left, 45 degrees off the right, 45 degrees off the tail, 45 degrees off the tail. And the signal comes in, and they use comparators to ascertain the azimuth that the signal is coming from. So the radar warning receiver intercepts signals from hostile radars and multiple wide coverage antennas, displays the threats to the aircrew. So I'll show you what the in a minute I'll show you what the display looks like.
Clayton,
Yeah. Mm-hmm.
can you just go back 2 slides?
Sure.
On the digital side, why are you saying that only handles one signal at a time?
I think what he's saying there is that it handles one per channel. So if you got multiple channels, you could process more than one. But if it's a single channel system, you can only process one. So the radar warning receiver does analysis on the pulses that it receives, and what it uses, the radar parameters, radar frequency, the pulse repetition interval, the pulse width. It analyzes scan pattern information, affected radiated power. It doesn't measure effective radiated power, but it measures the strength, the relative strength of signals. So if I have a very strong signal, it's going to show up, and I'll show you the receiver, what it looks like in a minute, but it'll show up as a strong signal. If it's a weak signal, it shows up as a weak signal. But it's not actually trying to measure the ERP specifically, it just measures relative ERP. The beam characteristics of the radar, we talked before about the fan song radar has this very, very specific fan beam pattern. And so that's an interesting beam characteristic. Some AAA radars and AI radars have a conical scan. So again, that's an interesting beam. And then sometimes there's an associated emitter. We talked about on the SA2 system, there was an associated emitter of that missile guidance system that's separate. And so that can be interesting information that can be passed to the air crew.
This might be a stupid question, but how can you measure the beam characteristics from you have a single system on your plane? You don't have any kind of spatial awareness of what the plane looks like.
Okay, let's say you've got a beam that's doing this. So you can measure that because it keeps beating back and forth.
Right.
And so it just measures that.
Okay.
If it's a conical scan, for example, if you're on the edge of that conical scan, you'll have a specific pattern. And then if it locks on you, what it does is get you in the middle of that pattern, and it'll be a steady sound. So the radar warning receiver display looks like this. It also gives you an audio signal as well. So you can hear what the radar sounds like, as well as see where it is. This represents the nose of the aircraft, and this, of course, is the tail. And this, it uses the Russian SAM notation. So here's a SA2 at 1 o'clock, and the relative strength is indicated by how far this is, how close it is to the center. If it's a very strong signal, it'll be down here. This is a medium signal. If it's weak, it's out here. It also draws a little box around the highest priority threat. So this would be an SA6 at about 3 o'clock, and that has been the radar warning receiver processor has designated that to be the highest priority threat. Here's an airborne intercept radar at 7 o'clock. That one's pretty close. I would actually say that's probably the highest threat, but in this case,
either way, it's not a good situation.
Unless it's your wingman.
Yeah, anytime you have an airborne interceptor close behind you, that's not a good situation.
Actually, on Andy's point about wingman, is this differentiating between blue and red or friendly?
Yeah, because the radar warning receiver can do that for you because it knows what the friendly radar parameters are, and so if the friendly radar is and it's not going to show it.
Okay.
And then this shows like a AAA threat, an anti-aircraft artillery threat at 9 o'clock. And then, like I say, it gives you an aural indication as well, so that the pilot or the aircrew can hear what that radar sounds like. And so, for example, like that fan song, with those two beams beating, that has a very distinctive sound. And so, oh, yeah. And then the other thing is, this doesn't show it, but you can have auxiliary threats. So, for example, the SA2, he's got that missile guidance system. And if you have the SA2 and then you suddenly have a missile guidance system illuminating you as well, that's not a good situation, So that's basically the idea of the radar warning receiver.
Clay,
Yeah.
would you typically put on the audio all the threats or just the priority one?
Now you'd have all of them.
Oh,
Yeah.
lovely.
And it's usually, you're not going to have, even with just that many, that seems like a lot. But you can distinguish,
yeah.
a trained operator can listen to it and say, oh yeah, this one and that one, yeah. That's going the wrong way. Oh, okay. And we talked a little bit about this before, but usually the radar warning receiver uses 4 very broadband antennas, and the kind of antenna that's normally used is a cavity back spiral. I'm sorry I didn't bring a picture of the cavity back spiral, but it's a little round antenna. It's got a spiral in it. It's very broadband, and so these guys, they have an RF bandwidth from around maybe 2 gigahertz up to 10 gigahertz. So they're extremely broadband. The antenna is mounted at 45 degrees, and they're also typically at a 15 degree below the horizontal. They're bore sighted about 15 degrees below horizontal, and that's because the primary threats that you're worried about are ground-based threats. The airborne interceptors, they're a threat too, and if they get close, they're a big threat. But if you have it pointed down a little bit, 15 degrees, you'll still pick up that airborne intercept signal if he locks on. Okay, so moving on from that to kind of the SIGINT approach. One of the things we want to do is we want to be able to do geolocation of the threats of the radars, of the emitters. And so there are different ways to do that. And this just kind of, you can spend days going through all the technology to do this, but this is just sort of a quick look at the different approaches. Triangulation, where you have, let's say, 2 different receivers that are receiving direction finding on a certain signal. And where they intersect is, where the best estimate of where the signal is. We can also use range and angle. If we have one kind of antenna that's used as a rotating antenna, and a rotating antenna will give you a strong return when it's pointed at the signal, and then not a very strong return when it's not pointed at the signal. And so it gives you some indication of azimuth, and if it's very sensitive, it can also give you an indication of range. We could also have multiple ranges, and that would show, if you had multiple receivers and they had a way to measure range, where those intercept would be the estimated location of the signal. We could have other approaches which are a little more sophisticated that may or may not be used. And then another very important piece of electronic warfare is what we call electronic attack. And it's the action part of EW. And so those are actions that are taken to reduce an enemy's effectiveness. And they can include jamming, deployment of chaff or flares, and transmission of energy to damage enemy sensors. It can also use kinetic energy weapons like anti-radiation missiles. The effectiveness of jamming is impacted by the geometry of the engagement, types of signals being used, and the electronic attack strategy. And we'll talk a little bit more about that. Jamming can be employed against both enemy communications and radars. Oops, sorry, that's wrong line. So this is a representation of kind of the theater electronic warfare campaign, if you will. You might have jamming aircraft. This is the EA-18G. This is the U.S. Navy aircraft that does standoff jamming. The RAF has, I think they use Tornadoes for that role. And you may have also an escort jammer. And an escort jammer is a jamming aircraft that flies in with a strike force. You could have specialized aircraft that do other kinds of jamming. We could have EC-130s, which do standoff jamming and communications. We have miniature air-launched decoys, and I'll show you that later. And they can fly in close and do jamming. The advantage of getting close for the stand-in jamming is that because of the space loss, the closer you are to the system you're trying to jam, the more effective your jamming is. So that's an advantage of the stand-in jammer versus the stand-off jammer. So we look at the jamming from a visualization point of view. We have a radar, and it transmits power from an antenna, which has a certain gain, and there's space loss as that signal propagates to the target. It impacts the target, and then the target has a certain gain to it depending on its radar cross-section. And then it re-radiates that energy back to the radar. So the radar signal has experienced an R to the fourth loss because it's got R squared going out, R squared coming back. The jammer, let's say it's out at the same place as the target, let's say it's on the target. It transmits energy, it has free space loss, goes to the radar. So it's got an R squared loss. So it's got kind of an inherent advantage over the radar in that it's got an R squared loss instead of an R to the fourth loss. But on the other hand, the jammer power is usually lower than radar. Radar is typically a much higher power. So the total signal is going to be the power transmitted plus whatever gains occur minus the losses. And then when the radar signal comes back and the jamming signal comes in, then you've got, and I'll show you this later, but you've got a J to S situation, a jamming power to the signal power. And if that J to S is positive, then the jammer is stronger than the radar return. If it's negative, radar returns stronger than the jammer. Okay, so if you think about the different kinds of jamming that can take place, when we jam radars, what we're trying to do is prevent the radar from detecting or tracking targets. For communications, we're trying to prevent the communication receiver from receiving information from the desired signals. So the jammer can be in different locations. Could be on the radar target. So if the target has its own jammers, that's called self-protection jamming. And it can be either cover jamming. Cover jamming, I'll show you a picture of it later, but cover jamming is when you just wipe out the radar. Deceptive jamming means I'm introducing false targets on the radar screen or radar sensor. If the jammer is remote from the target, it can be standoff jamming. We talked about standoff jamming a little bit before. And the jamming the aircraft beyond the lethal range. So we want the standoff jammer to stay out of the lethal range of the threats that it's jamming. For stand-in jamming, the jamming is closer to the radar than the target. And again, that is the most effective jamming technique if you can do it. Escort jamming, we have the jamming aircraft that fly in formation with the strike package. Modified escort jamming, we jam aircraft and stay in the hostile radar beam. And then the two we talked about a minute ago, cover jamming, deceptive jamming. Cover jamming reduces the radar's ability to detect a target. Deceptive jamming causes the radar to think it has a return that's good, but it's actually not. It's just a false target. So here's the basic idea of a noise jammer. We have the radar receiver, and of course has thermal noise. It gets a target return, and say we have noise jamming at this level, then the jamming to signal ratio is the difference between those two signals, or the ratio of those two signals, and that could be in dB. Typically, it's measured in dB. Oops. Barrage jamming, spot jamming. Okay, spot jamming. In spot jamming, we center the jamming signal on the radar signal. And so we try to get as much energy into the radar as possible. And so nominally, you get 85% of the jamming power into the receiver. So this shows, here's the radar signal and 3 dB bandwidth of the radar, and then here's the jamming signal. And you're never going to get all the jamming signal into the radar, but if you can get it centered well, you get about 85% of the jamming signal into the radar. And this technique is called barrage jamming. And here we have a situation where we have multiple radars, and we have one jammer, and we're able to open up the bandwidth of that jammer so that it covers all of those radars. So this is a less efficient approach, but it's an approach that's used when you have a dense signal environment. And then another technique that's used when we have a dense signal environment is swept jamming. In swept jamming, we have a spot jammer, and we sweep that spot jammer across a broad band so that it jams all the radars in a given band. And here's the idea of cover jamming. This is the old plan PPI scope, plan position indicator scope, which is not used very much anymore, but it's conceptually still the same idea. If you have enough jamming power that you swamp the radar, that's called cover jamming. So if we have self-protection jamming, we talked about this a little bit before, this is where the strike aircraft has its own jammer. And so it's jamming the threat. that it sees. For support jammer, we have a strike aircraft, and then we have a separate jamming aircraft that is sending a jamming signal to the radar.
On that, Clay,
Yeah.
do you think going forward will every aircraft, every kind of plane look to have its own jammer, or is it better to have specialised escort systems that are the ones that do the job?
Yeah, so most of the tactical aircraft have jammers on them now,
Mm-hmm.
but they may not be very powerful.
Okay.
And they may be specialized jammers that do deceptive jamming, for example. So having an escort jammer that has a more powerful jammer on it is helpful.
Yeah.
So probably going forward, it's going to be a little of both, I would say.
So little capability on everything, but still keeping
Yeah.
some specialised.
But have some specialized, yeah.
I guess it sort of depends on whether you end up getting broadband multiple function RF systems on the aircraft.
Yeah,
Because if you do, then the radar has much more jamming capability,
Mm-hmm.
yeah,
assuming you have a radar on the aircraft.
yeah, sure, yeah. So again, the idea of the parameter that we're concerned about is the jamming to signal ratio, which is shown here. If we got the skin return from the aircraft is here, and maybe the jamming is at this level, then the J to S is positive, and it's going to be, whatever it is. So the J to S ratio is the ratio of received power from the jammer and skin return within the bandwidth of the radar receiver. Another countermeasure is so-called chaff. And chaff was actually invented during the Second World War and was used extensively by the British, and the Germans, and Americans. And it was just, in those days, it was aluminum or tinfoil that was just cut in strips. It was, tried to get strips that were about the length of the wavelength of the radar so that it was resonant. And modern chaff is much more sophisticated, and it uses fiber, metal-coated fibers, and billions of little fibers in a chaff cartridge. And all bomber aircraft are going to carry chaff, and a lot of strike fighters will have chaff as well now. They may only have a few bundles of it, but and this is basically the idea of how chaff works. The radar signal impacts the chaff cloud, and it's scattered back. And if the radar RF is within the bandwidth of that chaff, it's going to give a large return. So it's going to look like a big aircraft. Another countermeasure for infrared is a flare. And this shows an aircraft, I think it's a Canadian AWACS, dispensing flares. And the idea here is if you have a fighter coming, very often the air-to-air missile that's used by fighter aircraft is infrared guided. And so if he knows there's a fighter behind him, he's going to shoot out those flares and hopefully cause the infrared missile to go to the flare. The flare is going to be very hot compared to the heat sources on the aircraft, the engines primarily. So hopefully the infrared missile will lock onto a flare. Those could also be used, they're used on ships as well. And they can be used to counter surface-to-air missiles. You know, there are these hand-launched infrared guided missiles that sometimes are used by terrorists and stuff around airports, and these kind of flares can be effective against those as well. Of course, most airliners don't carry them. Another countermeasure is the anti-radiation missile arm. And the anti-radiation missile is a passive missile. It has a passive RF seeker, and so it locks on, the aircraft locks it onto the threat that it wants to engage, and it will shoot it at the threat. And usually they try to shoot it in the side lobes, but sometimes they'll go to the main lobe of the radar. These were invented back in the 60s also during the Vietnam War. And the first one was called a Shrike. And the Shrike was a AIM-9, which was an infrared guided missile that they took the guidance package out of it and put an RF guidance package in it, shot it at the SA-2s. And it kind of worked, but it had several problems. One, it was slow. So the fighter pilots wanted to be able to outdraw the missiles. So they wanted to be able to, get locked onto by a missile and then shoot the strike at it before he shot at him. But it wasn't that fast. So that was a problem. It had a small warhead. So if it hit the missile site, it might damage the antenna, and that's about it. You'd like for it to destroy the control van, and kill the operators and everything else. But it was too small for that. And what else? I guess the seeker was not that great either. So the U.S. Air Force invested a lot of money in advanced techniques, and the one that's used now is called the HARM, the high-speed anti-radiation missile. And I'm pretty sure the RAF uses that as well. It's used, I think, pretty much by NATO. This is the HARM, AGM-88. And this is EF-18, and these are the jamming pods, ALQ-99 jamming pods. They have a ram air turbine that actually powers the pod, and they produce a lot of jamming power. Another countermeasure is a decoy, and there are basically three kinds of decoys. There are expendable, towed, and independent maneuver. So the missions then for the expendable are seduction and saturation, towed or seduction, and independent maneuver is detection, seduction, and saturation. And they're employed expendable by aircraft and ships, towed by aircraft, and independent maneuver by aircraft and ships. So the towed one, I know specifically one case, the Global Hawk UAV used the towed decoy. And I'll talk a little bit about the MAL, which is an independent maneuver system. So this shows the three different ideas of decoys. It can be towed by an aircraft, can be expended by an aircraft or a ship, or it can be independent maneuver.
Does the towed at some point disconnect and move on?
It could, yeah.
Unless
It
you've got a
would-
really
it-
long cable.
yeah, no, you're right. It would. They definitely would have to.
Okay.
Before you wanted to go land, you don't want to.
Well, yeah, okay, yeah. There is that, yeah. Dragging along.
This is an interesting system. It's called the MALD, the Miniature Air Launch Decoy. And again, I kind of think the UK has bought this now. It was developed by the U.S. Air Force, and the Navy bought it. And it's a pretty capable system. It can have payload. It can have an explosive payload, or it can have a jammer payload, or probably other things as well. Okay, the last thing I want to talk about just briefly is the idea of electronic protection. That's the third leg in the triad of electronic warfare. So electronic protection is applied to both radar and communications. So in radar, some of the electronic protection techniques are to reduce side lobe jamming using auxiliary antennas and cancellation circuits, or by adjusting the antenna beam. You can also do reduced deceptive jamming by special processing circuits or special modulations. And then you can attempt to reduce all jamming by using special operating modes. Communications electronic protection techniques are primarily spread spectrum. And spread spectrum, there are two types of spread spectrum generally. So-called direct sequence, where you just take the signal, the information signal, and you spread it out over a very broad band. And then the other is frequency hopping, where you have a fairly narrow band signal, but you randomly hop it around. Okay, now you guys are all experts on EW.